All right, let's dive into a mystery that puzzled scientists for nearly 100 years. It's a story about a strange, non-stop jiggle that, believe it or not, ended up revealing the hidden rules of randomness itself.
So, what do they have in common? It sounds like a riddle, right? But the answer connects the biggest and the smallest things in our universe. Turns out, everything from the afterglow of the Big Bang to the tiniest speck of dust is in a constant state of random motion. And for the longest time, nobody had a clue why.
So, let's rewind. Our story kicks off not with some brilliant discovery, but with a simple observation. An observation that created a puzzle that would stump the scientific community for almost a century.
Okay, so picture this. It's 1827. A botanist named Robert Brown is looking through his microscope at some pollen grains floating in a drop of water. And he notices something odd. The grains aren't just sitting there. They're jiggling, they're dancing around in this totally frantic, random way. He saw that this little dance never stopped, and if he heated up the water, they jiggled even more wildly. This strange effect got named after him, Brownian motion.
This was a huge mystery. You have to put yourself in the 1820s. The idea of atoms even existing was still really controversial. So without the concept of tiny, invisible things bumping into the pollen, there was just no good explanation for this endless, energetic dance. It was a complete scientific cliffhanger.
So the first real crack in the case doesn't come until 1905, during Albert Einstein's incredible miracle year, when he published 4 papers that literally changed the world.
Einstein's idea was, well, it was completely revolutionary. He said the pollen grain isn't moving on its own. Nope, it's being constantly hammered from all sides by billions of tiny, invisible water molecules. Think about it like a giant beach ball in the middle of a packed concert. Each person pushing on it is a small shove, but all those random shoves from every direction make the ball move around erratically. That's exactly what was happening to the pollen.
Now here's what was so clever about Einstein's approach. He knew that trying to predict the exact path of one single pollen grain was basically impossible. It was total chaos. So he didn't even try. Instead, he kind of zoomed out. He developed a statistical model to predict what a whole cloud of these particles would do. His famous diffusion equation could perfectly describe how that cloud would spread out over time. And for the first time, it gave scientists a prediction they could actually go out and measure.
And this is the bombshell moment. By creating a math model for this jiggling that people could actually test in a lab, Einstein gave the world the first real, concrete proof that atoms and molecules were real things. It was incredible. He'd found a way to see the invisible world, and it finally settled one of the biggest debates in physics.
But you know, science is rarely a solo performance. Around the same time Einstein was doing his thing, other brilliant minds were coming at this exact same problem from totally different directions.
Let's talk about 2 of them, Marian Smoluchowski and Paul Langevin. Smoluchowski thought about it statistically, kind of like Einstein, picturing the particle's journey as a random walk. You know, like someone taking a bunch of random steps left and right. That's a kinematic approach, focused on the motion. Langevin, though, he took a dynamic approach. He focused on the forces causing the motion, using the classic tools of physics. And Langevin's idea was just so elegant. He started with Newton's classic F equals ma, and then he just added 2 things to it. First, a drag force, because the water slows the particle down. And second, he added a brand new mysterious term, a random, fluctuating force to represent all those chaotic kicks from the water molecules. And what's so cool about this is that it's a perfect example of how different paths can lead to the same truth. You have Langevin's model focused on the forces hitting a single particle, and Einstein's model looking at the behavior of a whole cloud of particles, and they both predicted the exact same thing. It was this stunning confirmation that, yeah, they were definitely on the something real.
So Langevin's approach was beautiful and, as he put it, infinitely simpler. But there was a catch. The math behind his random force was pretty shaky, and it raised some really hard new questions for the mathematicians.
So here's the core of the problem. How do you use something like calculus, which is built for smooth, predictable changes, on something that is totally random and jagged from one moment to the next? This random force was so erratic that the normal rules of math just didn't apply. As one source put it, the physicists were being a bit cavalier. They were getting the right answers, but the mathematical foundation was basically quicksand. This is where 2 other physicists, Leonard Ornstein and George Uhlenbeck, step onto the scene. They saw how brilliant Langevin's physical intuition was, but they also knew it needed a rock-solid mathematical foundation. Their whole goal was to tame this randomness, to make it mathematically legit. And what they did was really smart.
They decided to treat the random force not as some big mystery, but as a statistical thing with defined properties. They made this key assumption, that the random kicks at any given moment have nothing to do with the kicks that came a moment before. By doing that, they built a totally rigorous mathematical framework. And this new framework didn't just confirm the old predictions, it could also describe the particle's motion at super short timescales. For the very first time, all the different approaches were finally united into one coherent, powerful theory.
So, why is this nearly 100-year-old story about jiggling pollen grains so important? I mean, what does it have to do with our world today?
Well, this whole story reveals something fundamental about how science works. Sometimes, solving one very specific, kind of weird puzzle gives you the keys to unlock 100 other ones. The math that was invented just to understand this one little jiggle, well, it turned out to be unbelievably powerful and universal.
Seriously, the study of these random or stochastic processes is now absolutely everywhere. That same background jiggle, that noise, is a critical factor in designing the computer chips in your phone. It's essential for engineers who are building microscopic machines. It even helps biologists model the random fluctuations happening inside our very own cells. It turns out our universe is just a fundamentally noisy place.
And that leaves us with this one kind of mind-bending final question. We learned how to predict the statistics of randomness, but we can never predict the random event itself. It's always there, at the very foundation of everything. So, in a universe that's built on a constant chorus of random jiggles and kicks, how much of our world can we ever really say is predictable?